Ano que vem, talvez seja ao vivo, não?
Se a gente sobreviver, sim.
Complicado.
Isso ainda tem... Isso ainda vai demorar mais um pouco.
Mais um. 6. Anthony Esteban. Joaquim, Henry, Fernanda Flores, Daniel, Eduardo, Carlos Salvatore.
Ok, gracias, Renato.
Quando o Renato entra, fica ruim, hein? O que houve?
Debe ser alguma... Un problema com o microfone, está acoplando, sei lá.
Onde ele está fisicamente?
Lima.
Lima. Tá bom. Mais 5 minutos.
Tá bom.
Temos poucos participantes até agora, hein?
Mas
Robert, você,
o pessoal entra, né, ao longo, sim.
Fernanda Flores,
Mais ou
Daniel,
menos
Eduardo.
às 3 da tarde o pessoal começa, não continua entrando, né?
Você tem que autorizar um a um, né?
Para o pessoal que não que não tem um e-mail institucional, ou seja, que não tem um e-mail da Uni, sim.
Eu acho que no Zoom você não precisa fazer isso, né?
Depende muito das configurações.
Imagina uma reunião com 2.000 pessoas.
Aí é um pouco diferente. Que nem no formulário, né?
Você está participando da reunião do Zoom?
Em algumas, sim. Hoje, não participei da foto, por exemplo, né?
Eu entrei, mas não sei se entrei a tempo. Tem uma mensagem de alguém aqui que passou. Qual é?
Hélio, você pode passar o material que você já tem feito?
Apareceu uma mensagem aqui, mas saiu.
Estão perguntando o que você já escreveu, o que você já fez, se tem algum arquivo. Robert,
Vocês não estão guardando o vídeo disso, da apresentação?
O vídeo, sim, mas acho que o pessoal gostaria de ter também os slides. Se puder, né? Robert, el material se va a ir colgando, los slides, sí, claro. El material se va a ir colgando. Todavía estamos moviendo esto porque el evento propiamente comienza mañana, pero ya debemos estar colgando el material en breve, ¿no? Por lo menos los videos de las clases.
Para você?
Sí, va a estar todo disponible, no te preocupes.
Robert, o escrito eu não tenho porque eu escrevo na hora. O escrito está no...
Talvez no escrito, mas...
Os slides? Sim.
Sim.
Os slides, sim. Eu passo para você e você coloca no ar.
Tá bom. Você passa para mim e eu coloco eu peço para o pessoal que faz isso, né, colocar lá na página do evento, né, do Meeting.
E os vídeos também? Como é que você faz?
Todo o material. Todo o material vai ser disponibilizado. Pode deixar.
Tá. Eu passo, então, a...
Dime, Renato. Aí.
Sim.
Muchas gracias, Renato. Viu, Helio? Pronto.
Ok. Muito bom, muito bom. Tá. Mas de qualquer forma, eu vou enviar a apresentação da segunda-feira, que é a única que eu tenho em PDF, as outras eu faço na mão. Um minuto. Anthony, Carlos Giovanni, Cristian, Daniel, Fernanda, Franz, Henri, Jesus, Jonathan, Joaquim, José Juan, Robert Guzman, Sérgio Oscar, e Dino Rodrigues. Não. Deixa eu pegar o meu material aqui. Opa, está na hora. Alô? Alô, não ouço.
Estou começando, vou começar a gravar.
So it's time now should start.
Okay, guys. Welcome again. Good afternoon to everyone. We are resuming the mini course of Feynman Diagrams. Okay. I just have one more announcement. In the middle of the lecture, I will be posting a link for you to fill out the attendance form, please. Okay. Please don't forget to fill out this form. Okay. Thank you, guys. Helio, please, you want to share your screen, please?
Olha, it's very bad now. I couldn't understand anything you said. Can you hear me?
Yes. Go ahead, please.
Hello?
Hello.
Okay, so your connection is very bad. Don't forget to... Hello. Don't forget once in a while to send me some signal saying that things are going well, you know, that we have not lost connection. Okay, good afternoon, everybody. I see that we have now about 20 people already connected. So what you have to do today? So yesterday, we went through a very simple model just to understand. I have to share my screen. Let me share my screen. A very simple model. Let me share my screen. Okay, 3, 2, 1, 0. So as I said yesterday, we went through a very simple model of a Feynman diagram, just for us to have an idea how to work with a Feynman diagram. So we had a set of Feynman rules that applied for that particular toy model. But what we really want to do is to have Feynman diagrams, basically for quantum electrodynamics. We don't have time for many other things. For quantum electrodynamics. So all we need to do to have is the Feynman rules for quantum electrodynamics. And then once you have the Feynman rules for quantum electrodynamics, you do pretty much the same thing we did yesterday, and you can then calculate the amplitude. However, the Feynman rules for the QED that applies for electrons and muons are not that simple before. So first, you must have a way to describe the electron, the muon, and the tau. And for that, we need some quantum physics. And particularly, we have to solve some Dirac equation. Okay, we, of course, don't have time to go through lots of quantum mechanics, let alone Dirac equation. So I could just throw the Dirac equation here and go ahead. That's to make things very complicated. So what I plan on doing, and I assume that everybody has some basic knowledge of quantum mechanics, but just to go very briefly through a few details of quantum mechanics. Then we get to the Schrödinger equation. Then we go to the Dirac equation. That's the one that you can. And then we're going to solve the Dirac equation for electrons or the leptons. And then we'll be ready to use all this information to work with some Feynman diagram. So, as I said, this will be very superficial. So I'm going to step several steps to go over several steps, but I try to make it a little bit understandable. So today is the 20th. What day is today? Today is the 22nd. Today is the 23rd. So let's write here. Start. Today is 23 September 2020. Lima. Okay. And okay, not that big. And as yesterday, here's my goodness. So if you have questions, just send me email, because many times more than one participant has pretty much the same question. So it's easy to send me the email, then I can give you a chance if you're talking. So just send me an email with your question. No, don't hesitate the question, please. So let's see what I have to do a little bit of mechanics. And I will enhance this little bit, just a little. So do not get scared, okay? So first we start with the thing that's non-relativistic. Okay, when I start non-relativistic, just to make things a little bit easier, because when you deal with the particle physics, we have to use the relativity, because all these particles are really, they travel so fast, and we cannot really have anything about the particles without considering relativity and quantum mechanics. So let's start with non-relativistic. So let me have blue. So what you have? Okay, basically in classical mechanics, you have the momentum of the particle in physics, classic physics, classical physics. What you have energy, and momentum. Just real numbers. And they so that's it. In classical mechanics, we have a body, whatever, we have moving, and we have its energy and its momentum, and the energy and momentum are functions of time. Okay, and we have kinetic energy, you have potential energy, and we know precisely what the energy and what the momentum of the system is. Okay, so that's not what happens in quantum physics. They go to particles like electrons and other things. We do not have a way to know exactly the position and the momentum. What you have in quantum mechanics is that you have here, we have a postulate. I write this as a postulate. That you have a wave that we call the postulate. So basically, if you have the proper thing, we have this So this is a wave, okay? The particle. So we should be able to get the information about the particle from this wave, okay? But how do that? So we don't have the energy and the momentum explicitly. We have the right side of the wave. See, you have momentum, you have the energy. Okay. So in quantum physics, this was classical physics. Now in quantum physics, okay, energy, let me change the color. Energy and momentum from okay. So from the wave function that represents the particle itself, we can get the momentum and we can get the energy. And how we do that? We do that through what we call an operator. So we have an operator. Sorry. An observer, as the name suggests, is something that you can observe. You can really see. So an observable A, how we get it is the action of an operator. So we have an operator, A hat, here, that when you apply this operator to the wave function, we should be able to get the energy and to get the momentum. So if you have the wave function, the way I show here, it's very easy for us to know what you have to do on this function to have the momentum and to get the energy. So basically what happens is that you have to apply the operator on the wave, and then we should have something like this. On where A, what's it called? Eigenvalue. And they are real for physical reserve. So then we should have an operator for the energy that when you apply to the wave function, the result will be A, that's an eigenvalue, times the wave function itself. As these A, the eigenvalue, are the possible values of that operator. Okay. In quantum mechanics, when you deal with the energy, many times the energy of the system may be a set of discrete values. In classical physics, it may be possible in a range. But in quantum mechanics, many times you have the possible energy are E1, E2, E3, E4, E5, whatever. So whenever you make an observation of that system to try to get the energy, you're going to have one of those values. The same may apply to the momentum. But then if you go back to this function here, you see what you have to do to have an energy, what you have to do to have a momentum. Look, this is an exponential. So to get E, all we have to do is to get the derivative of this exponential with regards to t, because as we all should know, if you have, let's say, the uh, see, the something that is E to, let's call, then it's easy to see that the operator for the energy would be I. Okay? And you get the derivative of the function with respect to t, you're going to have a function there multiplied by minus I and E. So my I times I gives exactly the energy. So if you apply this on the wave function, you get the energy of the system. And if you, for the momentum, we have that P will be like minus I okay? So in a very simple case, rather than have x like a vector, we may have just one dimension. There will be only x. So in this case, the momentum will be just be derivative which relates to x. So that's a very simple idea. Once you have accept that you represent the particle by a wave function, we may get the energy and the momentum simply by doing this very simple operation on the wave function. Supposing I have the wave function. And then we get the energy, all the possible energies of the system, and you get the momentum, or the possible momentum of the system. Okay. That's what usually takes us maybe 1 or 2 weeks in a quantum mechanics course to do, and we're doing it very fast. Now, but how do we get to this wave function that represents the particle? Okay? Well, how do we get to this for a particle? Okay, then there is a trick. So, in classic, we have that the energy of the system equals to T plus V, where this is the kinetic energy, and this is the potential. So a system has the energy of the system will be a kinetic energy plus the potential energy. If you have one body moving here on space, its total energy is the kinetic energy plus the potential energy. That's what we do when we have just a free fall of a body. Any other thing, very simple. Now, see, energy, E, the total energy, kinetic energy, potential energy. So what you do? Now, E, have the energy, and E, is equal to so I'm writing the kinetic energy as a function of the momentum plus V. So energy, momentum, plus the potential energy. And see, we have here the operator for energy and the operator for momentum. So what I'm going to do is just put them there. So how do we do for quantum? So in quantum physics, for quantum, what I do? Okay, in quantum physics, let's do. Right here, so I have more space. I'm just in one dimension, just to make it easy. This is E. Is equal to H operator because I forgot here. Let's write it here. So remember that you have H. We call H is equal to T plus V. That's what we call Hamiltonian. Okay, just T plus V. So it will be H then H is T plus V. So T, let's write it here, P2 2M plus the potential energy. And so this will be minus 1, so 2M. Great. So if we put everything then for one dimension. It will be, right, change the color. Let's say I just one dimension, just to make it a little bit simple. X T equals to minus 1, so 2M plus and this has to be so it was very easy to get the Schrödinger equation. Okay? We just start with the postulate that we can describe the particle by that wave function. Then we have the expression for the energy in the classical mechanics. And then you apply the concept of the operator for the energy, for the momentum, and then you get the equation. So if you solve this equation, means find the wave function, we know the wave function for that particular system. Of course, here depends, we have here the potential, V. Okay, that will change everything, depending on the particle you have, the mass of the particle we show here. So it was very easy to get the Schrödinger equation. Okay? And once we have the Schrödinger, we solve the Schrödinger equation, we have all the description, a complete description of this, our system. We suppose it. Of course, it doesn't mean the solving the Schrödinger equation is easy, but that's another point. Now, as I called attention at the very beginning, the Schrödinger equation here is not valid for relativity. And observe, we started with the expression for the energy here is a classical expression. So it's okay for classical physics. But if the system involved is a relativistic system, this equation does not work. Okay? So I think this is enough we need now for Schrödinger equation, just to understand how we get Schrödinger equation. And in the case of classical mechanics, we don't know exactly the position of a particle, for instance. The wave equation basically helps us to know the probability of finding the particle in a particular region of the space. Then, of course, if you take the whole space, that probability will be 1. So at some point, you should do a normalization in order that the whole integral of this probability should be 1. But we're not going to this detail now. Important to know is that once you have the equation, we can have the probability of finding a particle in some particular part of the universe, the probability of having the particle with some momentum in some part of the universe. That's how things work. And it's the universe, in many cases, would be just to say our lab, for instance. Okay? But anyway, you got that allows to get the wave function for classical. Okay? Now let's go some pages ahead. My notes here have several pages to deal with this kind of thing. And let's go direct to here. I have in page 8. So let's skip about 6 pages and see how we do now with the relativity. And for relativity. What to do for relativity? That's what we really need. Well, we're going to do pretty much the same thing. But here, see, we start the expression of energy in the classical physics. Now we're going to use the expression energy that comes from relativity. Okay? Now, then, in relativity, we have E2 is equal to P2 plus M2. Okay, and E equal to P2 to M plus V. This is classical. Huh? Here, I should call attention for a very important detail. Huh? In fact, the expression of energy in relativity involves the speed of light, c. So, in fact, we should have m2 and also multiplied by c, something, and p2 also multiplied by something, factor of c here. However, the speed of light is a constant. It doesn't depend on the frame of reference. It's always the same. C. So it's very convenient if you use the speed of light as a unit for measuring speed. The fact that the speed of light is about 300,000 kilometers per second, this is a strange number just because of the units that we invented, like a meter. Meter is something pretty much arbitrary. So once you define measurement of distance as meter, we came to the conclusion this light travels about 300,000 kilometers per second. That's a lot. But now that I know that the speed of light is a constant, it doesn't change the reference, it doesn't matter the frame of reference where you are, the speed of light is always the same. So it's much better if I use the speed of light as the unit to measure speed, rather than have meter per second or whatever. And in that case, then the speed of light, c, is equal to 1. That gives us the advantage of getting rid of c. So all equation that comes with the c will disappear because c will be equal to 1. Equation gets very simplified. Of course, at the end, when we get the results, and the result shows the speed of some particle, that result will be something like a 0.7, and 0.7 means 0.7 c. That part is going to 70% of the speed of light. Well, the speed, the result will not come in meters per second, but in a function of c. And then we have a much easier expression, like the energy square equals the momentum square plus mass square. So it's a very, and then the same way as I applied the operators for energy and for basically the momentum, I apply them to the expressed classical for energy, I'm going to do the same here. Okay? Then applying the operators for E and P, we have the same thing. I got to Schrödinger equation applying these operators to the classical definition of energy. I'm doing the same here. Then what I have is, change column. The hat means the operator for energy, okay? Okay. And then
Professor, your expression is for a free particle, yes?
what?
And the equation that you shown us is for free particle.
Not necessarily free particle, because the potential, see here, we have the potential here, the potential energy. So if you have a free particle, this potential energy will be zero, and then you have a free particle. Okay? Of course, it's much simpler to calculate if you don't have this potential energy here. So it's not necessarily required. That gives the following. There is some background noise now. Oh, okay. Equal to square okay, this is called Klein-Gordon equation. So that I can write the following way. So I'm going to just open this a little bit to just make clear what we're talking about. This is this is the Klein-Gordon equation. So this equation would be the equivalent of the Schrödinger equation, let's say this way, but it's a relativistic equation. Okay, I can write this much compact way using this notation here. Okay, so this is a way of writing this in a more compact way. So this is the Klein-Gordon equation. Now, this equation gives rise to two negative energies. And as I mentioned before, the wave equation should give us the probability of finding a particle somewhere. If we define an area of the space and you apply the wave equation, should have the probability. And the probability of finding a particle there should be some value from 0 to 1. However, okay, these negative energies, well, it's possible to make an interpretation of that. This negative energy, we can basically as what we call an antiparticle. So this thing, if you go to interpret this way, you can understand it as an antiparticle. And this negative probability is, of course, nonsense. We cannot have this. So there are some problems with this equation. Okay, if you start to deal with situations and you have this negative energy, so you have this what we could call antiparticle, we have a problem with this negative probability. What doesn't make sense? So this equation, although it's a relativistic equation, has some limitations. You cannot use it everywhere. So what is the solution? Well, then Paul Dirac comes for the rescue. So Paul Dirac was one of the greatest physicists that ever existed. And he was almost officially a madman. So he was strange. But being strange means that he could see things that other people would not see, imagine things, understand things that are not. And they pretty much came to this problem and produced what we call the Dirac equation. So what happened? Basically, we have here E2, E squared is equal to P squared plus M2. What that to the Klein-Gordon. And the Klein-Gordon equation is second order. In the second order equation, and for the t and x. And this is pretty much what is the source of those problems that I mentioned here before. So what Dirac went to do is the following. Dirac, as I told you, he was a strange guy, right? But very, very clever. E. Alpha, PT, plus first order. Yeah, for him was to find the values of alpha and beta that would satisfy the equation And they also be consistent with the Klein-Gordon equation. So let's write how this thing looks like. Remember, this is the operator for the energy equal then minus I this is writing out the operator for the momentum minus minus satisfies. So that to be the first word. Oh, whatever. My goodness. Here, my goodness. That equation, the relativistic energy momentum equation, and at the same time, if it satisfies the energy momentum equation, would be okay with the Klein-Gordon equation, but at the same time, be not to have those problems because it's a first order equation. That's what he's written here. This is a first order equation. See, there's no second order. It's not the second order, but it's not only the first. So that's very easy. Just solve this and see what happens. That's all. So if you make all this operation, you come to something horrible that looks terrible. But anyway, it's not as terrible as we look for. Okay. So if I open all that thing, that's what I get. plus second derivative from x and y plus I suggest you to try this. It's not difficult, just some algebra. Y z plus alpha z alpha x plus alpha x alpha z. Z x, and finally the terms that comes with beta plus I alpha x beta plus beta alpha x plus the same thing, but now with the alpha y. M. Now derivative with respect to y. And finally, alpha z m fantastic. So let's call attention to all this big thing here. Okay, so that's what we have. And I want this to be like the Klein-Gordon equation. The Klein-Gordon, I'll just repeat here, is equal to minus m. So for them to be the same, all we have to do is to see what the values of our x is. So this equation here, this huge one here, would be reproduced to the Klein-Gordon equation. So for that, that's very simple. If you look for them, you see that we must have alpha x squared must be equal to alpha y squared. That must be equal to alpha z squared. That must be equal to beta squared. It must be equal to 1. That's easy, okay? Not very difficult to do. Alpha x, alpha y, alpha z. It should be, the square should be 1. So they could be plus 1, minus 1. And then you have the alpha j beta plus beta alpha j must be equal to 0. And alpha j alpha k plus alpha k alpha j must be equal to 0. for J. Okay. Okay, that's what you have to see here. Okay. This first term here, the first term is like this one. So alpha x squared should be equal to 1. And all the other terms here must be 0. That's what we have here. Problem? Is there a problem here? Yes, there is a big problem. Not possible. It's really not possible? Well, Dirac was not a normal guy, as I said. Well, this is not possible. At least, not as long as alpha and beta are numbers. You don't find any set of numbers, real numbers, a complex number that could satisfy it. Listen, what's shown here that you have two numbers, alpha, j, and beta. So alpha j times beta plus beta times alpha j is equal to 0. That doesn't happen because we have numbers. A times b is the same as b times a. There's no way that could happen. What is showing here is that for this to be true, a times b must be the opposite of b times a. That doesn't happen with numbers. The same happens here. You have alpha 1, alpha x and alpha y times alpha y times alpha must be equal to 0. It means that alpha x times alpha y must be the opposite, minus alpha y times alpha x. Numbers don't do that, but matrix do. Okay? Numbers. But they could be, but what? But what if they are matrix? Okay? They're matrix. Because a matrix, you can have this. The product of two matrices, matrix A times matrix B, is not necessarily equal to matrix B times matrix A. So you may have a set of matrices that A times B is equal to minus B times A. And if that's the case, you can satisfy this case here. So we must have matrix. So if you go to matrix, you would have, say, alpha x squared plus alpha y squared plus alpha z squared equal, no, sorry. I made a mistake here. Equal to E. This I is not a number, right? Yeah, it's the identity matrix. For instance, for 3 times 3 matrix, it will be 1 0 0 0 1 0 0 0 1. If it's 4 by 4, it will be only ones in the diagonal and all the others in the. So if you may have this situation, and of course, alpha x, alpha y, alpha z are necessarily different, and then that means that they do not commute. Commute means that A times B equal to B times A means commute. But A times B is different from A, B times A. Do not commute. There's no commutation. So with numbers, that's not true. Numbers, A times B is B times A, but not with a matrix. So all we have to do, that has to be done, is to find a matrix that would satisfy the situation. We're not going into details, but let's put here the matrix that satisfies. So what comes that? 2, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, minus 1, and 0, and then 0, 0, 0, minus 1. Okay? Now, x will be 0, 0, 0, 1, 0, 0, 1, 0, 0, 1, 0, 0, 1, 0, 0, 0. Okay, of course, nobody has to memorize all these things. Some people do, but if any book that deals with the particle physics, we have at some point a list of all these matrices, okay? So we can write this in a more convenient way, just saying that, say, beta. So we don't have to write so many zeros and ones. And this one here, we may say that x is equal to 0, and of course, that means that is sigma x is equal to 0, 1, 1, 0. Okay? And the others are alpha y will be 0, 0, 0 minus I, 0, 0, I, 0, 0 minus I, 0, 0, I, 0, 0, 0. So not to write all these things, we say that this alpha y will be the same as, there's something here bothering me. 0 sigma y, sigma y 0. Okay? And again, this sigma y is 0 minus 1 minus e, 0. Those make it easier to write. And then this alpha z is 0, 0, 1, 0. Will 0, 0, 0 minus 1, 1, 0, 0, 0, 0 minus 1, 0, 0. And again, also for simplicity, z is equal to 0, z, z, and 0. Okay, this sigma matrix, this sigma x, all the sigmas we have here, okay? Sorry. The sigma is a direct matrices. Now, That's all. This is fantastic, and Dirk was really a genius. But there's a wait a minute. If the alpha x, you see, all the alphas and beta, they are not numbers, but they are matrix. What about here? Huh? This is a matrix. A matrix. A matrix multiplying by a wave function. How do we do that? Huh? Well, and here, see, on the other side, we don't have a matrix. This is the energy. So if we have a matrix here multiplying by this wave function, how can we have a number here on the other side? We don't. Well, what happens is that the wave function itself is no longer a wave function, but is a simple wave function. The wave function now, then, the wave function now will have 4 components. 1, 2, 3, and 4. That's okay, because if you have a matrix that is 4 by 4, okay, 4 by 4, 4 by 4, and you multiply this for something that's just 4 by 1, that results in just something that's 1 by 1. It's a number, basically a number. So all this solved the problem, creating another problem, of course. Because before we had just a wave function that would represent the particle. Now we have something that has 4 components. Four components. This is called the spinel. But anyway, let's change the color. It's a wave function with 4 components. That's called Dirac spinel. Means that you have 4 of them. Of course, this is a complication, but it solved this problem. Okay? So to describe a particle, like an electron, that is going to do, or a moon, or a tau, whatever, we don't have a simple wave function, but you have a wave function with 4 components. And then we have this Dirac equation that we have to solve. And once you solve, we have all these 4 components, and voila, we can describe the electron and whatever we want. So I'm not saying that this is simple, okay? I'm just saying that's how it is. And when you apply this to a Feynman diagram, you're going to do it in the most simple possible way, is that to avoid the complication. So putting everything together, I created this matrix in that is just I, 0, 0 minus I, okay? And the other matrix that's I, that should be so the Dirac equation will be I. Again, I'm using that notation just to make things shorter. writing something that's missing. No. I, H, gamma, V. Oh. Okay, so this is the direct equation. It looks very nice, very simple. Of course, solving the equation may be really complicated depending on the system we have. What time is it now, please? Let me check. Okay, we have some time. Okay, I know that this is scary, okay, but it's not that as bad as it may look like, okay? Just the way we show it is complicated. So what we have to do now, once we have this direct equation, is just to solve the direct equation for the case of an electron. And it's easy to understand that the solution for an electron is pretty much the same solution as for a muon. It's the same solution for a tau, because the main difference between electron, mu, and tau is just the mass. So the mass that shows in the direct equation will be the mass of the electron, the mass of the neutrino, the mass of the electron, the mass of the muon, the mass of the tau. So it's basically we have just one solution. Okay, and let's try to do it. Let's solve. When we deal with Schrödinger equation and we're going to solve the Schrödinger equation, of course, the equation is the same as always happens in physics. Although the equation is the same, the conditions are different. The initial conditions may be different, or maybe the boundary conditions may be different. So depending on the general situation solved, the equation may be complicated or maybe very simple. Quite often what we do is to take some simplifications. We solve the equation for a situation that's easier to solve. Sometimes don't solve it. We direct equation. Okay, let's take some simplification. Okay. Some simplification. And we want to avoid as complication. So let's say that my wave function x, y, z, d, in fact, is equal to our wave function depends on time, not x, y, and z. That's really not any absolute simplification because you are trying to describe the behavior of a particle, and it doesn't matter if it's here or there or any other place of the universe. Okay, so that's a simplification that is not going to be a big problem, and that implies that okay. And remember, this shows up here in our equations. Huh? So it'll be much, much simpler. There will be only the part depends on t. So okay, all those derivatives, that's what matter here. We're going to have the following: I, H. Notice that the H slash is also a constant. Okay? It shows a lot in quantum mechanics, the Planck constant. And since it's a constant, the value also depends on the system per units that you just decide to in our life. And most of the systems are arbitrary. You just decide this is 1 meter, this is 1 second, this is 1 kilogram. There's no reason for that. But since the H slash is a constant everywhere, rather than have it defined from starting from the other constants from the other units that you define, you use it as the unity. The same way as we did with the C, where C was defined as having the value 1, and so we get rid of C in the equation. We may also define H slash the Planck as 1, and they have everything else in function of it. So it'll be, that makes things much easier, okay? This is the direct equation. Reminding us that this is not the right this way. And then we have those forms, just repeating here. Minus y, I 0, and 0 minus 1. Okay, so if you go to solve this, my Apple Pencil is not working well, and I do not understand why it's not working well. So let's see. Here we have the derivative in function of t, x, and so the derivative between the t, x, y, and z. Okay, that's what we have. But in fact, all the problems, at least we can see a little bit from relative, that's something that we are not going to see much, but we can have all this representing a particle, a position. We need the information about this time, x, y, and z. So in general, what you have is that you don't call this necessarily t, x, y, and z. You use something more prosaic, like x0, x1, x2, and x3. Yeah? X0 stands for the time, 1 for x, 2 for y, and for z. Then the equation will look like that. I, H slash, eventually I'm going to get rid of the H slash and from C. So this 0 here is meant the derivative in front of p, okay? Plus gamma 1 Then, as I mentioned, the function, the wave function has 4 components. Then let's put the 4 components there. And then you have I o que está fazendo? So this is right. Is written right x, y, z into here. And here you have 1, 2, 3, and 4. Minus m c 1, 2, 3, and 4 equal to 0. Okay? So, if we make this multiplication, we multiply this, but those, we have a set of basically 4 equations to satisfy, right? Because when you multiply this, you get just one expression, and you have to solve for all the 4 components of the wave function. So let's put this in a more compact way. Let's say 1, 0, 0, minus 1. This is the, remember that, okay? This gamma 0 function. Here, in fact, this 1 here, in fact, this is a 4 by 4. They are all 4 by 4, man. So here, where we have this 1 here is the unitary unity matrix, okay? 1, 0, 0, 1, and the opposite. So it's a 4 by 4 matrix. So here we have it. I put I just to make it clear, okay? Here I need more, so this is too small. I b squared C squared, and they have H slash. If both are equal to 1, they just will disappear. So these two things here, used for a question of simplification, these two first components. So these are the two up components and the two down components. So once we have, we can go for some calculation. I'm going to just start it because there's no time today to finish everything. But so I'm going to try to solve this. And solve this is not difficult. So you just multiply things. So if you make the multiplication, a matrix multiplication, first you multiply line times row times row. So here we have okay. Okay? That's what we get here. Okay. Those are very easy. It's very easy to solve this equation. It's a differential equation, but it's very easy to resolve. Okay. So here we have in fact, here is something wrong because here should be a, no, it's correct. Okay, minus and minus. And the second one, the solution for B, is also the differential equation within this, with the solution. Basically saying here that the derivative of the function is the function itself times a constant. This is an exponential, right? So pretty much the same, but without the minus sign. I P. Okay, we have two solutions. Solution for the two components at the top and for the two components at the bottom. Okay. Okay. So what you do now? So that simplification made at the beginning, consider that the function depends on x, does not depend on x, but just on t, made it much easier for us to calculate it. But E. That is basically a state. So from quantum mechanics, we know that this component here, this thing here, shows the dependency of a state with energy. So how it evolves with time, how it goes with time. Now, if you have a particle or a particle at rest, we have that E is equal to mc squared. That famous equation. Okay? That's rest. So if it's rest, the only energy of the particle is the energy of its mass, is the rest mass of the particle. So the particle at rest, that's what you have for energy. So this here is what is expected. P equals Q. And these other components, the energy, there's energy. Sorry. Because this will give E equals to minus mc2. Huh? Now, there comes again, Dirac again. Okay, we have a particle with negative energy. What the hell is that? Basically, Dirac comes again. And then we have what we call Dirac. C. Basically, the idea, no matter how crazy it may look like, is that we have a C going everywhere. Okay? And let's see if we can remove a particle. It's like you take the particle out, then there is a hole in that place. So, and both have existence. The particle we remove is the particle itself, and the hole, there will be a negative opposite, a negative particle. There will be the antiparticle. So the way to understand that is that once you create a particle and you pull a particle from this sea that exists there, then that ocean that's everywhere, you also produce a hole. Okay, remove something, and there's a hole there, and the hole itself has existence, has meaning. What you remove is the particle, say like an electron, and what stays there is the antiparticle. It's the opposite. You remove an electron that has a negative charge. So if you took a negative charge out, then the result there is positive. So you have something positive there. You remove a particle with some mass, that's the electron. So it's there is the opposite of this. So it's the same mass with negative charge. The energy will be negative. That's what shows here. E equals to minus mc squared. So this Dirac-Mar provides the solution for antiparticle. Well, you're going to say that this is crazy, and you are right. This is crazy. And when this idea came out for Dirac, people said, well, this is no sense. This is just mathematics. Okay? There is no such thing. However, not long after this, people really observed what's called the antiparticle. So not long after that, people could observe in laboratory a particle that was exactly pretty much like an electron, except that it had a positive charge. And then they start seeing particles that looked exactly like a muon, but they had a positive charge. So it was exactly the opposite of the electron. And as we mentioned before, if you have this electron and the positive, they come together, they annihilate. There is annihilate each other. So what came as just maybe a crazy mathematical idea from solving all these equations, and came a negative energy in some interpretation. That was the interpretation. And at first it could be just a mathematical thing where people found out very, very fast, and for many people they were surprised that those particles that were are now called the antiparticle did exist. So that what started was just a theoretical approach, and that proving to be very effective, very able to describe what you really see in nature. And that's what physics does. Yeah? Physics does not explain why things happen, does not explain, does not answer why, but just how things happen, how particles interacted, how things, if you drop an apple, the apple goes to the floor. Okay, so physics will describe this process, but why is another thing. So we observe what we call antiparticle, and the name antiparticle is just an invention of us, because at first we knew everything, and everything was, of course, matter. So when we find something that was the opposite, we go, well, this is antimatter. Okay, in principle, they are both matter. Let's say like that. I could, the same way that we say the electric charge of an electron is a negative charge, and then the opposite is positive. It could be the other way around. When people found out about charge, what they realized that there were two kinds of the same thing. One they said is positive, the other is negative. When both get together, they have zero. It could be the other way. So it's pretty much arbitrary what is negative and positive. But once we define that, so that's it. We call something matter, the other is antimatter. So today, because I think we saw already a lot, and I hope nobody has just given up. And tomorrow we'll continue with the solution, because we don't have yet the solution for the electron and for the muon that we need for the Feynman diagram. So we're going to do that tomorrow. There's not much to do now. We are very close to have a solution to really solve these things here, and then use it for Feynman diagram. Okay, I understand today was quite heavy, because this is not the kind of thing we see in 2 hours and less than 2 hours. It should take some time more for people to master this kind of thing. But anyway, we don't have much time, so some of the things we must just accept to understand. But if you take the bibliography that I have produced, you can see this is some more detail. And of course, if you have all the books, to go through all the quantum mechanics there, but quantum mechanics itself requires at least 2 semester courses, a lot. So pretty much this, I hope that this helped at least to understand how we came to the Dirac equation. The Dirac equation describes particles from a relativistic way and satisfies all the relativity energy relation, and how from that we came to this crazy, strange idea of having a matrix rather than numbers, and then the wave function that in principle is just a wave function has 4 components. And then once you solve these 4 components, we see that we're going to have some of them represent some states with negative mass, and this we interpret as antiparticle. And once we solve for the psi A and psi B, we have 2 components for electron, and of course 2 components for the anti-electron, both of them. And what happens to electrons, that the electrons have a spin half-a particle. So when you have an electron in a system, this electron may have its spin up or its spin down. So basically the spin could be aligned with the movement or the opposite way. So in fact, we end up with 4 possibilities. The spin, electrons to spin up, electrons to spin down. Anti-electron, positive spin up, and anti-electron to spin down. 4 components, exactly what you have here. So the 4 components of the wave function, and each one of them we're going to have 4 solutions, 4 different. So one will be for the spin up, the other for the spin down, one for the positron up, the other one for the spin. Of course, we're going to use whatever. If we're going to work with problem with the spin up, we're going to use the solution for the spin up or for the other 4. And of course, in a situation, we may have 4 different answers. We're going to do only for 1 case, okay? And a later more complicated one for you to try to do home. Okay, I hope that you have got some understanding of all this subject. And tomorrow, we'll go a little bit further, and then you're going to be ready to deal with Feynman diagrams. Is someone still about has given up? Oh, yeah.
Okay. Hello. Okay. Many thanks, Helio.
Okay.
Okay.
Well, so we meet tomorrow. We meet tomorrow again at the same time.
Yes. So if you have any question, please send an email to Helio.
Meet again tomorrow at the same time.
Yes, please. See, tomorrow. Yes.
Yes, please. Yes, you have a question. Please send email. It's much easier, and I answer. Okay. So meet you tomorrow.
We could meet tomorrow. Yeah. And thank you to everyone for attending today's lecture, and see you tomorrow. Take care. Thank you.